Welcome back, everyone. It's the 19th lecture of the condensed matter course, nearing the end of 6th week. I know it's hard to keep going on at the end of 6th week. Everyone gets pretty tired, but we're really getting pretty close to the end of this course now, so it's power on through. So when we left off last time, we were talking about magnetism, and we decided a good place to start thinking about magnetism was one atom at a time. So we're really thinking about atomic magnetism. And we had written down the Hamiltonian, actually the Hamiltonian for one electron in one atom in a magnetic field. And we decided we would write it as the Hamiltonian for that electron in zero magnetic field. That's just the kinetic energy and the attraction to the nucleus, plus two terms. The first term is Bohr magneton, magnetic field, dotted into orbital angular momentum plus g spin angular momentum. And the second term, E squared over 2m A squared, where A is the vector potential, del cross A equals B. Okay. Now these two terms have names. This first term over here is known as the paramagnetic term. And this term here is known as the diamagnetic term. And as you might guess, it's this term that's typically responsible for paramagnetism, and this term which is typically responsible for diamagnetism. And this term, it's actually fairly obvious why it is that this term is going to be responsible for paramagnetism. Generally, this is just coupling of the magnetic field to the spin or orbital angular momentum of the electron. And okay, now it's a little complicated because of the minus signs, but the spin wants to, or the orbital angular momentum, both of them want to point opposite B such that the energy of this becomes negative. And if the spin or orbital angular momentum is opposite B, that means the magnetic moment is the same direction as B because the charge of the electron is negative. So the moment points opposite of the angular momentum. So anyway, in order to lower the energy, the spins line up opposite B, and the orbital angular momentum lines up opposite B, and therefore the moment lines up in the same direction as B, and you have paramagnetism. Now, one thing you may notice about these two terms is this paramagnetic term is linear in B, whereas this term is quadratic in B. And so generally, for small b, the linear in B, the paramagnetic term, is going to dominate. As long as there's not a particularly good reason why the paramagnetic term is going to be suppressed or somehow even zero, then the diamagnetic term is irrelevant, and we just have to worry about the paramagnetic term. We will find occasions where this term is zero or is suppressed, and then the diamagnetic term will have a chance to dominate the physics. But we're going to focus on this one first, figuring it's going to be more important. So let's take this term. And what we're going to want to do is we're going to want to simplify it a little bit. Now, one thing we can do is we can add together the angular momentum of the orbital angular momentum and the spin angular momentum to get the total angular momentum. J is L plus sigma. But you'll notice that's not what we actually have in the Hamiltonian. We have L plus G sigma. Now, you may have learned or you should have learned in your atomic physics course, that under conditions where you know the magnitude of J, the magnitude of L, the magnitude of sigma, you can rewrite that entire term in terms of some effective G factor, G effective, known as the Landé G factor, usually written with a superscript J, mu B, B dot J. And there's some formula that allows you to get the effective G factor from G and the magnitude of J and the magnitude of L and the magnitude of sigma, if you know these. That formula is not part of this course, but I believe it's part of your other course, so you probably should know it if you're taking the atomic physics course. You won't be asked to derive it in this course. You may be asked to derive it in the other course. At any rate, the moral is that you can put together the orbital and spin angular momenta, and under the conditions that you know what J, L, and sigma are, you can just think of this as a singular angular momentum vector that reorients in a magnetic field, and the entire term can be summarized as this. So it's a fairly simple term in the Hamiltonian under those conditions where we can just think of it as a single total angular momentum being reoriented by the magnetic field. But in fact, the story is a little more complicated than this. And it's more complicated than this because we have many electrons in an atom, many electrons in atom, not just a single electron. And that means we have to keep track of the entire angular momentum, capital L. That's the sum over all the electrons of the orbital angular momentum of each electron, and then the total spin angular momentum, which is the sum of all the spin angular momentums of each of the electrons, and of course, the total angular momentum altogether is the total orbital plus the total spin. And as you probably learned from your adventures in Clebsch-Gordan coefficients, that you can have very complicated ways of adding together angular momenta. For example, two spin 1/2 can add together to make a singlet or a triplet, and then things get really messy, and if you have 20 electrons in your atom, they can add together in all sorts of crazy ways. And so we need something to guide us to figure out how it is that these electron angular momenta are going to add up. First thing that we have to guide us is the shell structure of the atom. So let's remember back to the beginning of the term, shell structure. We had two laws that helped us out. The first was the Aufbau principle, which basically, Aufbau, which in German, I believe, means building up or construction. It means you fill up shells one at a time. And the second principle we had was Madelung's rule, which told us in which order we should start filling shells. So that's going to help us out a lot. And the reason that's going to help us out a lot is because there's an important principle that a filled shell has L equals S equals J equals 0. No angular momentum at all in a filled shell. Why is that? Well, we filled every orbital with a spin up and every orbital with a spin down, so the total spin is 0. The number of ups is equal to the number of downs. How about L's? Well, we've filled all the LZ positive states, and we've equally filled all the LZ negative states in a filled shell. So the LZs all cancel each other, and the total L you end up getting out is 0. So a filled shell has no angular momentum at all, and that means we only look at part-filled shells. Look at part-filled shells. Okay, so that's going to help us out a lot. But still, you can have a part-filled shell with 3, 4, 5, 6, 7 electrons in it in a partially filled shell. If it's a big shell, you could have 13, 14 electrons in a partially filled shell. So this could still be pretty complicated. Fortunately, we have a set of rules that helps us figure out how these angular momenta add together. And these are known as Hund's rules. Hund's rules, after Friedrich Hund. And he wrote them down actually first in 1925, a very long time ago, back in the early days of quantum mechanics, just when people were learning about shells of atoms. Now, I may not know what Ansatz means in German. I may not know what Aufbau means in German, but I know that Hund means dog in German. So whatever that's worth, these are the dog's rules. But so rule one. Rule one. Electron spins align. Align if they can. If they can. In other words, you maximize S. All right? So this is actually a very nice rule because it's kind of like being a ferromagnet. In a ferromagnet, you get all your spins to align, and you maximize the total spin. It's not really a ferromagnet because we're just talking about a single atom here, so it's just a finite number of electrons, not a whole big solid of electrons, but at least has the same qualitative physics. So can we understand why it is that the electron spins would want to align? Well, okay, so why? Why rule one? Well, the first thing, it is not because of dipole interactions. Dipole interactions between the spins. Why not? Yes, the spins do have dipole moment, and the dipole moments will interact, but if you try to calculate the dipole-dipole interaction strength between two dipoles whose dipole moment is a Bohr magneton in a single atom, it's insanely small. It's so small you can just completely throw it out. Totally irrelevant. So it's not because of this. That's important to keep in mind. What it is due to Coulomb interaction. Due to Coulomb. Let's see if we can figure out why Coulomb interaction would care if the electron spins were aligned or not aligned. Well, so if you open up most solid-state physics books or most physics books of any sort, they usually tell you some story about why it is that electron spins want to align and why it is that Hund's rule is obeyed in this respect. And the story is sort of qualitatively right, but it has a lot of things wrong with it, so this is a warning. I think I gave a lot of caveats in the book, so you can read the details. We'll go through this a little bit. Well, I'll tell the story first. I'll tell the fairy tale first. Then I'll explain to you why the fairy tale isn't exactly right, so you'll have a better idea of what actually is going on. So in order to figure out why it is that Coulomb interaction cares, let's recall that if you have a wave function for 2 electrons, that wave function should be decomposed into the orbital part, which depends on the position of the 2 electrons, and the spin part, which depends on the spins of the 2 electrons. Now, the overall wave function must be antisymmetric because electrons are fermions. And so that tells us that if chi spin equals having both spins pointing in the same direction, like up, up, down, down, or both pointing sideways, if the spins are aligned, then this is then symmetric. Then the orbital part, psi orb, is antisymmetric. And what that means is if we write psi orbital as a function of R1 minus R2, we take R1 to R2, the wave function has to go to 0, because if you take an antisymmetric function and you take its argument to 0, the function must go to 0. Anything antisymmetric has to go through 0 at 0. So what does that mean? What that means is that electrons cannot get close to each other. Cannot get close. Close to each other. And you might think that the Coulomb interaction would care about that. And indeed, that's the story that's usually told. So the story goes kind of like this. If the spins are aligned, then because of the symmetry of the wave function, the electrons can't get close to each other. And that makes the Coulomb interaction happy, because the Coulomb interaction doesn't want the electrons to get close to each other either. So the energy is naturally lower because the electrons are staying farther apart from each other. Okay? It's almost right, but it's not really right. And the reason it's not really right is because really, more important is the electron nucleus, not the electron. And it's sort of a very subtle difference between electron nucleus and electron because it's all Coulomb interaction at the end of the day. But let me try to explain what I mean by this. So let's imagine we have a nucleus here, and then we have 2 spins whose spins are anti-aligned. So because the spins are anti-aligned, they can get close to each other. And in particular, one electron can get in between the other electron in the nucleus. Okay? Now remember when we went back and we talked about electronegativity and ionization energy, when one electron can get inside the orbit of the other, it can screen the nucleus, it can screen the electron from the nucleus and make the effective nuclear charge look smaller. As a result, the electron on the outside is weakly bound because it sees a smaller effective nuclear charge. On the other hand, if you align the spins of the electrons, then the electrons can't get close to each other, and in particular, this electron cannot get inside this electron's orbit, and it can't screen this electron from the nucleus. So as a result, the electrons are strongly bound. And this is more of the reason of why it is that that it's lower energy to have the 2 electron spins aligned, because then the 2 electrons are strongly bound to the nucleus, and that lowers their energy. Okay, so that's more of the honest reason why Hund's first rule applies. Okay, so we can even generalize Hund's rule up from atoms to molecules if we want. So suppose we have a molecule, Suppose we have a molecule with 2 positive nuclei and say 2 electrons up here. It's exactly the same physics. If the 2 electron spins align, then the electrons have to stay apart from each other, and they can't screen each other from the nucleus. Whereas if the spins are anti-aligned, then they can get inside of each other and they can screen the nucleus, and the binding is weaker. So Hund's rule wants the spins to be anti-aligned. Hund's rule still wants spins to align, even in a molecule. But that has to compete with something else. And the other thing that it has to compete with is the covalent bonding. Bond wants anti-aligned. Anti-aligned. Let's recall what we learned about covalent bonding. When we had orbitals on two atoms, both with energy E0, when the atoms come close together, they form a bonding in the anti-bonding orbital. And we want to put both electrons in the anti-bonding orbital, we have to anti-align their spins to make a singlet and put them both in low energy state. So there's a competition between Hund's in molecules. There's a competition between covalent bonding physics and Hund's rules physics. One of them wants the spins to align. One of them wants the spins to anti-align. So it's a lot more complicated in a molecule to figure out if spins align or if they don't. So one should just be aware that those two are competing with each other. Okay? All right. So that's Hund's first rule. It tells us that the spins will try to align if they can. So if you have a shell that's less than half filled, you can put all of the electrons pointing the same direction. When you get to half filled, you have to start putting electrons in the opposite direction because you've filled all the states with all the electrons in the same direction. But to the extent that they can, the electrons will always try to align. Now, that said, we still have to figure out what happens to the orbital degree of freedom. So rule 2 is very similar, which is basically L is maximized 2, subject to rule 1. To rule 1, which is more important. So let's see if we can do an example of this. Probably the easiest way to explain this is to show how it works. So let's consider a praseodymium atom. This is atomic number. Atomic number is 59. Number equals 59, which in 56 equals filled shells. I think it's filled shells up to 6s, actually. So that means we have filled shells plus 3 electrons. OK, so 59 equals filled shells plus 3 electrons in the F shell. 3 electrons in 4F in, well, just F shell. F is L equals 3. Remember SP, D, F, G. So F is 0, 1, 2, 3. F is L equals 3. So we can write out all the orbitals. Let's see, for F, L equals 3, there's 2L plus 1 orbitals going from LZ equals minus 3 to plus 3. So let's write them all out. So LZ equals, we have minus 3, minus 2, minus 1, 0, 1, 2, 3. Minus 3, minus 2, minus 1, 0, 1, 2, 3. And we have to put 3 electrons in those orbitals. Now, the first rule, Hund's first rule, says that the electrons we put in have to have their spins aligned. So we know we have to have aligned spins. And then what we want to do is we want to maximize L subject to the condition that all the spins are aligned. So we can think, well, let's try to maximize LZ. And we would do that by putting the electrons as far to the right as possible. And we would get LZ equals 6, 3 plus 2 plus 1. Now, we can also try to put them as far to the left as possible. And we would get the smallest value of LZ possible, which would be minus 6, minus 3, minus 2, minus 1. Okay? So if the largest LZ we can get is plus 6 and the smallest LZ we can get is minus 6, it means that the L we have, L equals 6 in this case. Okay? Good? Now, we can also write down S immediately is 3 halves. 3 spins all aligned is S equals 3 halves. So that's how Hund's rule works. And Hund's rule, second rule here, is also driven by Coulomb interaction, but there aren't very good cartoon pictures to explain why it is that L is maximized in Hund's second rule. So I apologize about that. It's just it's an observation that Hund made, and no one's really come up with many very simple explanations for it at this point. OK, so this tells us almost everything we need to know, but we still have the question of how does L align or anti-align with S. So we have rule 3. Rule 3, Hund's third rule, which is either L is parallel to S, or L minus L is parallel to S. And the way it goes is that J, absolute value of J, is absolute L plus or minus absolute S, where we choose minus if less than half filled shell, less than half filled, meaning that the spins anti-align with their angular momentum, and with their orbital angular momentum, and choose plus if more than half, if more than half filled. Okay, so that's Hund's third rule, which tells you how the orbital and spin angular momenta either align with each other or anti-align with each other. Now, so for example, in this case here, praseodymium, we have less than a half-filled shell, so J equals 6 minus 3/2. We choose the minus sign because it's less than half filled, and that gives us J equals 9/2. Okay, so we know everything there is to know about praseodymium. We know what an L is, we know what S is, we know what J is from Hund's rules. Okay, so why is Hund's third rule true? Well, Hund's third rule is actually a little bit unlike the other two because it's not driven by interactions. It's actually driven by something else. It's driven by rule 3 is from spin-orbit coupling. Spin-orbit, which is actually a relativistic effect, spin-orbit coupling. And in fact, it's basically that when we wrote down the Hamiltonian, we left out a small term, the spin-orbit term, which takes the following term. So I'll write it as delta H, a small piece of the Hamiltonian we left out, which we can write as alpha, sum over all the electrons, orbital angular momentum of the electron, dotted with the spin angular momentum of the electron. Okay? Now, in this Hamiltonian, alpha is greater than 0. And so, I mean, you can sort of see that this is going to make the orbital angular momentum and the spin angular momentum counter-align to make this as negative as possible. You're going to have, if the spin is up, the orbital angular momentum wants to be down and so forth. But you then might wonder, well, what about this business about half-filled shells and less than half-filled shells and more than half-filled shells? That seems a little bit strange. It turns out that that little strangeness is actually just from bookkeeping. You just have to be careful about the bookkeeping. Every electron that goes in is always following the same rule. Follow Hund's rule 1, follow Hund's rule 2, and then try to make this as small as possible. And if you follow that rule, you will always get Hund's rule 3. Let's see how that works for a second. Let's consider a case where we have, I don't know, a D shell. So in a D shell, we have LZ equals minus 2, minus 1, 1, 2, 3. Yeah, LZ equals minus 2, minus 1, 0, 1, 2. Those are the possibilities. And let's put one electron in. If you put one electron in, well, okay, it's pretty simple. It wants to maximize its spin angular momentum. So the spin, well, it only has one choice. It's spin 1/2, so that's easy. And it wants to maximize its orbital angular momentum as well. So we can put the electron way over here or way over here. Now, if you want to minimize the L dot sigma, if we make the spin spin down, then you would put it over here so that sigma z equals minus 1/2, but LZ equals plus 1/2. So the product of sigma dot L is negative, which is what we want. We want to make that term as negative as possible. Okay? And then sure enough, the sum of these two, JZ, is LZ minus sigma z, LZ plus sigma z is 3/2. And as claimed, it's a less than half-filled shell, so J is the difference of 2 and 1/2. Okay? So that works. Basically just telling you that when you add, you have less than half-filled shell, the spin and the orbit want to be pointing in the opposite direction, so spin dot orbit is negative. That's easy. Okay, now what happens when we get to a half-filled shell? When we get to a half-filled shell, LZ, we have equals minus 2, minus 1, 0, 1, 2. We have these 5 states. Now, once we're at a half-filled shell, we have to put in all 5 spins aligned because we want to align all the spins. So here we have S equals 5/2. 5 spins all pointing in the same direction. But L here equals 0. because we filled all the negative states and all the plus states as well. Okay? So here it's no problem. I mean, Hund's third rule doesn't even apply because L is 0, so spin is just yeah, absolute J is just a spin angular momentum here, so we don't have to worry about L. Now let's add one more electron. So when you add one more electron, LZ equals here we go, minus 1 out 4, 5, minus 2, minus 1, 0, 1, 2. We put all these guys spin down. We add one more electron. Where does that one electron go? Well, okay, it still wants to satisfy this condition that it wants its own spin angular momentum to point opposite its orbital angular momentum. So it has to go and spin up. So we have to put it over here. So this last electron we put in has sigma z equals plus 1/2, but LZ equals minus 2. And that still makes it happy because sigma z is pointing opposite LZ. But now notice what's going on here. The total SZ is actually still negative. It is actually negative what? It's negative 2, right? So the last electron that I put in was pointing up. The total spin is actually still pointing down. So, and even though the LZ is here is minus 2, the total, because the half-filled shell had LZ total equals 0, we added one electron. That electron is pointing up, but the total spin angular momentum is still pointing down. So here, the total spin angular momentum and the total orbital angular momentum are now pointing in the same direction. And we were still just following the same rule that each electron wants to counter-align his spin and his orbital angular momentum with each other. So in other words, the reason we came to this bookkeeping problem is because when we have a half-filled shell, we have S, which is non-zero, but L is 0. When we add one more electron, the net spin of the whole system is pointing in the opposite direction of the spin of that one electron we added. So that's why Hund's third rule has this complication at half-filled shell. Is that clear? Yeah? Hopefully? Okay. All right. I'm sorry that I mean, I know it's confusing, but that's the way life is sometimes, so we have to deal with it. Okay. So given that we know L, S, and J, we can then write down our Hamiltonian. Well, first thing we can do is we can take L plus GS, do the same Landé G factor trick, and rewrite that as some G effective times J, where J is L plus S. And then we can write down our effective Hamiltonian for these angular momenta, which was G effective J mu B B dot J. And we can do statistical mechanics with this kind of Hamiltonian. So to remind you how this works, this is something that you did last year. So example, let's take a really simple example. Let's take J equals 1/2 and a G factor of 2. So a spin can point up. With this overall angular momentum can point up or can point down. And the two possible energies are then plus and minus Bohr magneton times magnetic field. We can then write the partition function for this system, which is the sum over the two states of the angular momentum, e to the minus beta mu b b plus e to the plus beta mu b b. From the partition function, I hope this all looks familiar. We can write the free energy, it's kBt log z. We can write the magnetic moment. Magnetic moment is, I guess with the minus sign. Did I miss a minus sign here somewhere? Yeah, there's a minus sign missing here. Free energy. We can then write the magnetic moment, dF dB, which I believe you did this last year, and if you didn't, you'll do it this year again. Beta mu bb. It has this tanh form. For small b, this becomes just beta mu b squared times magnetic field. Then the magnetization, capital M, which is moment per volume, is the moment per spin, m, small m, times rho, the density of spins. And then we can get the susceptibility, chi, which is by definition mu naught dm dB taken at b equals 0. And if you go through that, take that limit, you get rho mu naught mu b squared over kBt, which hopefully maybe looks familiar from last year. This is known as Curie's law. Curie law. In fact, more generally, Curie's law is any time when the susceptibility is some constant over T, which indeed this is. So the important thing to notice about this Curie law susceptibility is that it diverges at low temperature. You have a divergent susceptibility as temperature goes to 0. And this is actually correct, and it's meaningful. The reason the susceptibility diverges at 0 temperature is because at 0 temperature, the system is always in the lowest energy state. So if you have a bunch of spins and you have a tiny magnetic field, no matter how tiny that magnetic field, there's a lowest energy state where the moment is aligned with the magnetic field. So even with an arbitrarily small magnetic field, the moments all align and point that direction, which means you then have an infinite susceptibility because it takes only an infinitesimal magnetic field to orient all the spins in the same direction. Is that clear? So this is actually a meaningful statement. When you raise the temperature, then the spins start fluctuating all over the place, and they don't all point in the direction of the magnetic field. I mean, they may point sort of vaguely in the direction of the magnetic field, but not all exactly in the direction of the magnetic field, so the susceptibility drops as you go to a higher temperature. Now, more generally than this simple spin 1/2 calculation, for spin j in general, we follow the same story, except we start with a partition function, which is sum over jz equals minus j to plus j, e to the minus beta, the energy of the spin in state j, which is g effective for j, then mu b b jz. I think I implied here, without stating it, that that b is pointing in the z direction, that we apply to b in the z direction. Otherwise, we would use a different axis, and it would be j. If we put b in the x direction, we would just use a different basis where we count jx from minus j to j. Sorry about that. OK, then you go through exactly the same manipulations. The algebra is a little bit more difficult. You get out some more complicated function than a tanh. It's a function known as a Brouillon function. It's some messy thing. I think you calculated it last year in your stat mech course. It has some hyperbolic sines and hyperbolic cosines in it. It's a little more messy, but the same story comes out at the end of the day. At the end of the day, you still get a Curie law in the sense that it's a constant divided by t for exactly the same reason. An infinitesimal field will orient all of the moments in the same direction. Okay? Now, one thing actually to note along the way, which is quite important, is a little bit of an aside, is to note that this partition function is a function of b over t only. It's not a function of b and t separately. Okay? And that's actually important because it means that the entropy will also be a function of b over t only. And that was noticed way back in, I don't know, the early 1900s by one of our heroes, Peter Debye, who has shown up several times already in this course. And he noticed that that would mean that you could do the following experiment. You take a system in a magnetic field at a given temperature. If you adiabatically reduce the magnetic field, adiabatic means that the entropy has to stay fixed. If you adiabatically reduce the magnetic field, the temperature must change proportional to the magnetic field. This is what's known as adiabatic demagnetization. Demagnetization. And it's actually a really good way to make a refrigerator, a very powerful refrigerator. You take a system at some temperature in some magnetic field, you reduce the magnetic field, and in order to keep the entropy fixed, changing things adiabatically, the temperature must reduce proportionally to the magnetic field. This is the way people build some of the world's most powerful refrigerators that get down to millikelvin or even microkelvin temperature. So it's a good thing to know about. And eventually, the technique breaks down, and it basically breaks down when our simple approximation of just independent spins and this partition function being right eventually breaks down at very low temperatures. We'll come to that in the next lecture or the one after, I think. All right. So this is basically the story of paramagnetism, one atom at a time. But when you start putting together many atoms at a time, things can be different. There's this phrase that goes around the condensed matter community. More is different. Whenever you put lots of things together, you can get different physics. So I'm still going to think, in some sense, one spin at a time, or one electron at a time, one atom at a time. But when we start putting it in the environment of a bunch of other atoms, things can start changing. So what can be different? What goes wrong, and what is different in a solid? What different in a solid? Different in a solid. Okay, a couple things we can write down immediately. One, we can have electron hopping. Electron hopping. And if electrons hop from one atom to the next, we expect to get band physics. We expect to get electron band physics, bands. And if you have a partially filled band, you have a metal. So band physics, you can get a metal. And if you have a metal, you expect to have Pauli paramagnetism, and therefore Pauli paramagnetism. You get a Fermi surface and Pauli paramagnetism. And if you have Pauli paramagnetism, the susceptibility is smaller by a factor of roughly kBt over EF. And the reason for this is that you still try to flip over spins when you apply a magnetic field, but you have to obey the Pauli exclusion principle, and that prevents you from flipping over a lot of them, and so only a small number of them will flip over in a magnetic field. Okay, so that's one thing that can be different. If the electrons are hopping from one atom to another, then you might expect to have a metal and Pauli paramagnetism and a much smaller susceptibility. So you might ask, well, when do we have no hopping? When is there no hopping? Is there no hopping? Because, you know, why would they ever not hop? Why would the electrons ever not hop from one atom to the next? Well, basically, this comes from interactions. When there's strong interactions, and we discussed this before when we talked about Mott insulators. I'll remind you what a Mott insulator is. Mott insulator is when you have one electron in each site, and due to the Coulomb interaction, it prevents you from ever having two electrons on the site. And then you have this idea of a traffic jam of electrons where there's one electron on each atom, and no one can jump to his neighbors because there's already someone sitting there. So everyone's frozen, but it's frozen with only one electron on each site, and so you can worry about that electron's spin or orbital angular momentum, and that can be reoriented, and it makes a very nice paramagnet that way. So these Mott insulators at at least at high temperature, we'll talk about them at low temperature in the next lecture, the one after, make fairly good paramagnets. So that's point one, what can be different in a solid. Point two of what can be different as a solid is that the environment can matter. Environment can matter. And to give you an example of why that can be, let's imagine that you have an atom in a long tetragonal unit cell, which is much taller than it is wide. And you might imagine that in a tetragonal unit cell like this, due to the environment, the orbital angular momentum might want to be pointing up or pointing down directly. Might want L pointing up or L pointing down, and not in the middle. So even if it was an F electron, which could point in LZ equals, you know, all the way from -3 to +3, it's still, because of the environment, it might prefer to point directly up or directly down and not anywhere in the middle. And that can change the story quite a bit. This is what's known as crystal field splitting. Field splitting, where the environment of an atom tends to fix which angular momenta are allowed and which ones are not allowed. Okay? And one thing that happens in this case, which is particularly important, is sometimes you can get a situation where crystal field, this is actually quite common, forces L to basically be 0. Make some sort of superposition of L's that force them to be 0, in which case, which implies that the total J is just then the spin S, and L doesn't contribute. So even if you had F electrons or a partially filled F shell where there's lots of electrons, and you might imagine that it would have a non-zero L by Hund's rule, because of the environment of the atom, L can be forced to be 0, and then you would only get the spin angular momentum and not the orbital angular momentum. This is typical of transition metals. I should tell you what it's called, of transition metals. Things like chromium. This is known as, give it a name, it's known as quenching of L, when L is basically removed from the problem due to the environment of the atom. It's typical of transition metals, but does not occur for rare earths, for rare earth or lanthanides and actinides, earth atoms. And the reason for this is a little subtle, but actually not that complicated. The reason for this is that in a transition metal, the partially filled shell is, say, the 3D shell. So here we have an atom, and it's maybe the farthest out shell that's filled is 4s. The partially filled shell is a 3D shell like this, 3D shell like this. And the 3D shell is very close to the outer edge of the atom in the transition metal. This is transition metal. And so the partially filled shell sees the environment of the atom quite strongly because the electrons are very close to the boundary of the atom. Whereas in the rare earths, you can have something where the outermost shell is something like 6s, and the partially filled shell is 4f. And so it's very protected from the environment because the partially filled shell has a much smaller radius than the atom as a whole. So basically, the partially filled shell doesn't even see the environment because it's so shielded from the environment by the larger orbitals in the atom. So it more or less explains why it is that the rare earths don't have quenching of angular momentum, whereas the transition metals do. All right, so this is everything we have to say, more or less, about paramagnetism. Let's back up to the first equation we wrote on the board here today and worry a little bit about diamagnetism. So when can we get diamagnetism? When is there diamagnetism? Well, there are a couple of ways that you can get diamagnetism. The first sort of classic case of when we get diamagnetism is when J equals 0. When you just so happen to have a situation where there's no angular momentum to reorient. There's no paramagnetism because there's no J. And for example, if you have a filled shell, like a noble gas, that would have L equals S equals J equals 0. And you can't reorient any magnetic moment because there is no magnetic moment to reorient. So in that case, you can basically just throw out this term in the Hamiltonian. The only thing left is the diamagnetic term of the Hamiltonian. Another case where you can get diamagnetism, I should also mention that not only you can have filled shell, you can also have filled molecular orbitals. Which, similar, like I mentioned this when we talked about van der Waals bonding. You have an inert atom like a nitrogen 2, an inert molecule like a nitrogen 2 molecule, which you can think of as being just a bunch of filled molecular orbitals. So it has a net J equals 0 at the molecular level. And so there's really nothing to reorient in the case of a nitrogen 2 molecule because all the molecular orbitals are filled, sort of analogous to a larger atom with orbital shells that are filled. There's another situation where you can get diamagnetism, which is when you have polyparamag. Polyparamagnetism is weak. It's always weak because its chi is smaller by, I wrote this down above, by kBt over EF, which is a pretty big factor. So if you have a metal like copper or something like that, you would expect it to be a paramagnet because it has spins to reorient, but because of the Pauli exclusion principle, they don't reorient very well, and you only get a very small susceptibility, in which case the diamagnetic term has a chance to compete with the paramagnetic term. And so here's a challenge. You should ask your tutors, is copper a diamagnet or a paramagnet? And unless they were tutoring this course last year, in which case students asked them the same question last year. So for new tutors, most of them will get it wrong. Most people will say that, well, it's a metal, so it's a polyparamagnet. And indeed, it has the polyparamagnetism physics, but that's so weak that the diamagnetic term here actually has a chance to compete with it. And in fact, for copper, it turns out to be diamagnetic, surprisingly enough. So you can, with metals which have only polyparamagnetism, you can get diamagnetism winning overall. So challenge your tutors with that. See how many get it right. All right. So very quickly, I think we can do this in 5 minutes. We can calculate the effect of this diamagnetic term. So the part of the Hamiltonian we're interested in is e squared over 2m a squared. And we'll put b in the z direction. So b equals b z hat. And so we can write a vector potential 1/2 b cross r, so that del cross a equals b. And that will then be b over 2. I guess we'll write y hat x minus x hat y. It's convenient enough. So this term in the Hamiltonian we're interested in is then e squared over 8m b squared x squared plus y squared. Then the expectation energy of this term in the Hamiltonian, which if we're doing this at 0 temperature, which is convenient to do, that's the change in the energy is the same as the change in the free energy, a squared over 8m b squared expectation of x squared plus y squared. And so the magnetic moment is then minus d expectation of energy dB, which is then minus b e squared over 4m expectation of x squared plus y squared. Now remember, in the last lecture I mentioned to you that diamagnetism is a little bit like Lenz's law. It's like a loop of wire. And when you have a loop of wire, the amount of magnetic moment you get from a current going around that loop of wire is proportional to its area. And indeed, this expectation of x squared plus y squared is the area enclosed by the orbital of the electron. So it's quite analogous to Lenz's law. It's really measuring the currents going around the atom in the same way that Lenz's law gives you a magnetization associated with the current running around the loop of wire. Calculating x squared plus y squared isn't so difficult in a spherical atom. So if we have a spherical atom, most atoms are spherical these days, we can write that as then 2/3 of expectation of x squared plus y squared plus z squared, or 2/3 of expectation of r squared. And so we can then rewrite the magnetic moment per atom here is minus b e squared over 6m. That 6 comes from putting together the 2/3 with the 1/4 there, times expectation of r squared. And then the magnetization is m times rho, where rho is the density of electrons in the entire system. And that gives us, well, we differentiate that with respect to the magnetic field. We'll get right here, chi equals mu naught dm dB, which is then minus mu naught e squared rho, size of the atom, expectation of r squared, divided by 6 times the mass of the electron. And this is known as the Larmor result, or sometimes Larmor-Langevin diamagnetic term. This is Larmor or Langevin diamagnetism, and that's the expectation of this. Now, in the remaining 2 minutes, I'm going to tell you something that's not examinable. This calculation is very standard for exams, calculate the diamagnetism of an atom or some system of atoms. There's something that's non-examinable, which is that we were a little bit too fast in throwing away the paramagnetic term. The reason we were too fast, we initially said, well, the paramagnetic term is linear in B, the diamagnetic term is quadratic in B, so we'll treat this term first, and then only treat this one if this term happens to be small. But actually, we should be a little more careful that we should worry about this term at second order as well. That if we were careful about it, we would have to also write some term that looked like this, second order perturbation result, n not equal to 0, of n mu b b dot L plus GS 0 squared. This is also quadratic in magnetic field, E minus En. This term is manifestly negative. The sign of the second order perturbation theory is manifestly negative, and so it would actually give us a paramagnetic contribution, paramag contribution. It's known as Van Vleck paramagnetism. Van Vleck, after Nobel laureate who discovered it. It tends to be small, but it can occur in particular in cases when J equals 0, but L and S are not equal to 0. So we have J, or L equals S, but J equals L minus S equals 0. And the reason it can occur is because if you remember, when we went back here and we said that we could replace this term in the Hamiltonian with J, the sum of these two terms, we were actually presupposing that the magnitude of L, the magnitude of S, and the magnitude of J were fixed. But in fact, you can have excitations where you unfix those, where you rotate L and S away from each other and change the value of J in the excited states, and you can get a non-zero contribution of this. And so it doesn't tend to happen for noble gases, because in noble gases you have L and S both being 0, but there are some elements on the periodic table which are, I think it's 1 less than half a filled shell, where L happens to equal S, and the combination by Hund's rule is 0, and this term can actually come out and give you a paramagnetic contribution as well. That's not examinable. Don't worry about it. It's just for your general edification. We'll talk more about magnetism tomorrow. See you then.